So, when we talk about synthesis, okay, we start looking at it from the the bird's eye view. You look at from the top, for a particular problem, and this is something, if you happen to end up in a core engineering job, you might have a task for which you need to design some task of motion transformation, or for which you may need to design a mechanism. So, the first thing you are going to look at is what kind of a mechanism do I want for this. Okay. It could be a linkage, it could be something that uses robots, it could be something that uses like a conveyor, it could be something that uses like a chain, a pulley, rope mechanism. You have a wide variety of machine elements to put together to form mechanisms. Okay. So, that forms the basis for type synthesis, and it is something that comes through experience. So, you would have seen similar applications, or you would so what you would do at that point is basically research similar applications, see what kinds of mechanisms are used for that, and then try to narrow down to the type of mechanism you want to use for the application. There may be cost considerations, space considerations, maintenance considerations, whole bunch of factors that will play into what you determine as the type of mechanism you want to use for your application. And a lot of that basically comes from experience. So, here we are not really going to deal with that aspect of it. In this particular course, our understanding is that, okay, I want a linkage for I think a linkage would be best suited for the applications that I am looking at. And so, the first thing that we do when you look at, if you want to look at a linkage as your solution, is to do the number synthesis, which is what we looked at earlier, which is basically determining the number and order of links and joints which you want to use to achieve the mechanism of required mobility. So, again that is something we looked at in the last couple of classes. Now, we come to the crux of this course, which would be the dimensional synthesis. So, once you have determined that a linkage is what you want, you know what sort of what mobility you want for your mechanism. In many cases it may be a 4 bar or a slider crank or some combination of that. Now, what you want is to determine the dimensions of the links in order to solve your particular problem, in order to achieve the particular task that you are looking at. So, that is dimensional synthesis. So, you have specific motion characteristics, that is what you are designing for, and you want to determine what should be the link lengths for that particular linkage that you are going to design. So, dimensional synthesis can be further classified into the following. You have what is known as motion generation. So, in motion generation, you want to guide a rigid body through a certain number of specified positions. Okay. So, here we are talking about both the position and orientation of that rigid body. You want the rigid body in the plane located at a certain point and oriented in a certain way, and you want it to go through a series of those positions, and you may or may not want to coordinate it with the input motion. So, these types of problems are called motion generation problems. Then you have what are known as the crank rocker diode synthesis, driver diode synthesis problems, where you have the mechanism. So, in many cases here we are talking about, we will first look at a 4 bar, okay, we will first look at a 4 bar. So, a 4 bar can be designed for motion generation, a 4 bar can be designed for, as a crank rocker, obviously we have seen the Grashof criterion. So, this is also called the limit position or dead center synthesis, where you want the output to attain 2 limit positions, to move between 2 limiting positions. Okay. So, you want the motion to be restricted, the input motion may be continuous, okay, in the case of the crank rocker synthesis, but for that input motion you want the output to be limited to 2 extreme positions, and this could be attained with or without quick return. So, you could say that when it goes from position A to position B, it takes a certain amount of time, and then from position B to position A may be faster. So, in many cases if you have a stroke where you are doing some work, say you are pushing something or you are cutting something, then you want a slower speed, but for it to again do that job again you want it to return quickly. So, you may actually have a quick return or a non-quick return kind of mechanism in these types. The third type of synthesis we will look at, the problems that we will look at will be the function generation problems, where you are actually coordinating again the motion parameters of the input and output link. It may be angular displacement of input link with that of the output link. Essentially the previous one is also an example of function generation, your crank rocker. You are coordinating the motion of the crank to the angle of the rocker or the displacement of the stroke of the slider crank. So, those are also function generation problems, but a special type of function generation problem. So, in this you are essentially the motion parameters could be, apart from displacement, it could also be velocity and acceleration. So, you may want the for a certain velocity of the input link, you want a certain velocity of the output link. Similarly with accelerations. So, we will see some methods of synthesis that will allow you to do that. So, that category of problems are called function generation problems. The fourth category is where you have a point on the floating link, which is the coupler, which follows a certain prescribed path. Okay. You want it to follow a certain prescribed path. You may recall the example I showed you of that film strip mechanism, where you had a point on the coupler which followed a certain path, and you may want to design a mechanism to do something like that. Okay. So, there the objective was the path of that coupler point. So, if that is your design objective, then we classify the problem as a path generation problem. Now, this classification, yes. Motion generation, you are looking at both the position and the orientation of the link in the plane. In the path generation, you are looking at only the path of a point on the coupler. Okay. So, that is the difference between the two. Now, a 4 bar does not really care what kind of problem you are solving. Okay. You may have all of these, you can design a 4 bar to achieve any of these tasks. The 4 bar's behavior is in, it's going to behave as a 4 bar, it has a certain relationship between the links, its coupler points move in certain ways, all that. Okay. The classification is only based on the problem that you are trying to solve. Okay. So, in most cases we are designing a 4 bar and the 4 bar behaves the way it does. We are trying to narrow down which characteristic of the 4 bar we want for our particular problem. Okay. So, that is the classification. So, it may be the same linkage that will so any 4 bar irrespective of what you design it for will have dead centers, will have limit positions, right. There will be some relationship between the input and the output motion. The coupler will attain certain positions in the positions and orientations as the 4 bar moves, okay, and the coupler points will trace certain paths. Okay. What you design the 4 bar for will depend on your problem classification. So, this classification is actually based on what you want for your application. So, that is the synthesis objective. So, this classification is based on your synthesis objective. So, this classification is based on objectives. Okay. Okay. So, let us look at, we will start off with 2 position motion generation. Okay. So, I have this, I have a rigid body, a link which I want to move from A1 B1 to A2 B2. Okay. That is my design objective. I wanted to attain this position first and then move it to this position. So, essentially I want to, so if I look at these 2 positions of a rigid body, okay, I can actually identify a point on the plane for which that position does not change for the 2 positions of the rigid body. Okay. So, if I extend these bodies, okay, then I find that, so how do I do that? Okay. Say I want to move this in a, do you remember Chassel's theorem? Any planar motion can be decomposed into a pure rotation, right. So, in this case if I want to try to do that, say I draw the, let me do it here itself, I think I have another figure here. So, if I look at A1 to A2, I draw the perpendicular bisector. So, this is the perpendicular bisector A1 to A2. So, I know that if I pick a point on that, that is going to be equidistant from A1 and A2. Similarly, I do that for B1 and B2, and the point where these 2 perpendicular bisectors intersect. So, this is, let us call this B12, the perpendicular bisector of B1 and B2. The point at which these 2 intersect is called the pole for these 2 positions. Okay. And what that tells me is, suppose I extend this body, okay, I make this a triangle A1 P1 2 B1, then this P12 does not move when the body moves from the first position to the second position. So, in other words, if I pivot the body at P12 and rotate it about that, then I achieve the orientation A2 B2 by means of a pure rotation. Okay. I achieve it by means of a pure rotation. So, if I look at this, then the rotation. So, OA1, sorry, not OA1, P1 to A1 has rotated to P1 to A2 by a certain angle, and any line on this rigid body is going to rotate by the same angle. Okay, I am rotating about a fixed point, any line on this rigid body is going to rotate about that same angle. So, P1 to B1 also rotates by theta 1 2 here, theta 1 to 2. So, actually for 2 position motion generation, I do not really need a 4 bar, I do not really need a linkage. If I can just find the point P1 2, okay, in a reasonable location, I can then pivot that body about that point and achieve this motion by a pure rotation about the pole. Okay. But in many cases it might happen that the pole is in a location that is not really accessible. Okay. So, it may not be possible to locate the pole and pivot it at the pole in order to achieve these 2 positions. Okay. So, in that case what do we do? You see here, so if you look at a 4 bar, if you look at a 4 bar, this link OAA and OBB are pivoted about fixed pivots. So, these A traces an arc, B traces an arc centered at the respective fixed pivots. Okay. So, when you pivot, it traces an arc. Okay. So, that means the 2 positions of A lie, so the center of rotation will lie somewhere on the perpendicular bisector of A1 and A2. Okay. So, if I pick my OA somewhere on the perpendicular bisector of A1 A2, then A1 will move to A2 along an arc, right. Similarly, again for B1 B2, I pick a point on the perpendicular bisector. So, if I locate my fixed pivot there, then I get my 4 bar linkage OA A1, A1 B1, B1 OB. Okay. So, when OA A1 moves to OA A2, B1 OB B1 will move to OB B2. Okay. So, here now I have gotten, because my pole may not be accessible, I can do the same 2 position motion generation by means of a 4 bar linkage. Okay. And I am using the fact that A and B, the locus of A and the locus of B both lie on arcs that will be centered around the fixed pivot. So, I can locate my fixed pivots for the 4 bar on the perpendicular bisectors of the positions of the 2 points. So, this gives me, so when I pick the pole as my solution for achieving this movement, then I only have a unique solution, because there is only one pole for the 2 positions. So, it is very limiting in that sense. Instead, if I want to design a 4 bar for the same thing, I can pick for OA, I can pick any point on the perpendicular bisector. I can locate my OA anywhere on the perpendicular bisector, which gives me an infinity of choices, because it all has to lie on that line. Okay. So, I can pick a point that lies on that line. Similarly, for OB I have an infinity of choices. Okay. So, I say that I get infinity square solutions for the 4 bar to achieve this 2 position synthesis. Of course, other constraints will come in which will limit the number of solutions that you eventually come up with, but theoretically I could have infinity square solutions for this problem. Okay. I could also choose to do this with a slider crank. Remember, the slider crank is only a limiting case of a 4 bar. So, that means in this case I say B1 B2 is my path, my straight path in which the slider block will move. Okay. So, here I will just, I have B1 and B2, I draw the perpendicular bisector. So, essentially I draw the path which is perpendicular to that. Okay. So, in this case only 2 positions, so it is a straight line, does not matter, I do not really need the perpendicular bisector. Then for A1 A2 I locate OA somewhere on the perpendicular bisector of A1 A2, okay, which is this one. So, I get a slider crank. Now what happens? I still have an infinity of solutions based on where I pick OA. However, my slider path now becomes fixed. Okay, B1 to, if I choose to do this with a slider crank, then my slider path is fixed because the pivot for that is at infinity. Earlier I had an infinity of solutions when I could take, if I wanted a finite location for the pivot. Now I have only one solution which is at infinity. So, that becomes a straight line. So, I lose the choices in terms of that. So, the number of solutions that I have is an infinity of solutions based on where I locate the pivot OA. Okay. I could also do the other thing, I could instead make A1 A2 depending on what I want as my input. Okay. I could make A1 A2 as the slider path and then pick OB anywhere on the perpendicular bisector B12. Okay. Again an infinity of solutions are possible because of the flexibility in choosing OB. What do you think is the next option? Both sliders, only one solution, right, becomes a unique solution because this is also at infinity, that is also at infinity. Okay. So, if these are guided, then A1 B1 will move to A2 B2. I can add. One thing that we have not looked at here, okay, is with any of these mechanisms, it will achieve A1 B1 to A2 B2, but we do not really know what is happening in between, that is one thing, and we do not know that these two are limiting positions. So, it may go past on this side or this side, you are not really looking at how the linkage behaves beyond here also. I am saying it will achieve A1 B1 to A2 B2 if I use this 4 bar, but there is nothing to say that it will only move between these 2 points. These two are not limiting positions that I am looking at. In many real life applications, you want your design positions to be limit positions. You want to pick something up, place it there, orient it, do something. So, and you do not want the linkage to then move beyond that, interfere with something else, or do other things. You want these two typically to be limit positions. So, one interesting thing that we will look at, So, here depending on, so here I chose OA and OB like this with respect to the pole, and if I look at the angle subtended by the coupler A1 B1 and the frame OA OB at the pole. Okay. So, I draw these triangles. Okay. I have A1 P12 B1 . I have OA P12 OB. Okay. If I look, so I can say this here is the angle subtended by the coupler at the pole. Okay. And then I have OA OB subtending this angle at the pole. Okay. Now, tell me, if I look at, this is the perpendicular bisector of A1 A2. Okay. So, this angle here this angle, what is it equal to? Theta 12 by 2. Okay. Then this angle similarly here OB P12 B1 again is theta 12 by 2. Okay. This angle is also theta, and this angle is common to both this part. So, this angle, the blue arrow, equals the red, equals that angle. That is, at the pole the angle subtended by the coupler is equal to the angle subtended by the frame. Okay. This is something that we will use later, or they will differ by 180 degrees. So, if you happen to choose OB on this side, then you will find that they differ by 180 degrees, the two angles. Okay. And you can also show that the crank and the follower subtend. So, here you have, obviously you can see the crank subtends an angle of theta 12 by 2. Okay. OA P12 A1 P12, that angle is theta 12 by 2, which is equal to the angle subtended by the follower, the rocker. Okay. So, the opposite links subtend the same angle at the pole. The frame and the coupler subtend one angle at the pole that are equal or differ by 180 degrees. Similarly, for the crank and the follower. This is something we will come back to later, and we will use this for function generation synthesis. Okay. The poles give you a very elegant way of synthesizing for function generation, this fact about the pole. So, we will come back to that later, but I just wanted to mention it at this point. Do you see here? Look at this figure. Okay. Do you see why this angle is theta 12 by 2? You see that? Okay. Similarly, this angle is theta 12 by 2. You see that from this one? Now, this I just showed you theta 1 2 by 2, this is again theta 1 2 by 2. This part of the angle OA P12 B1, this part is common to both, right. So, this angle is theta 1 2 by 2 plus this x, which is equal to this plus this. So, the two angles are equal. Okay. So, coupler and frame, crank and follower, opposite links, they subtend equal angles at the pole or angles that differ by 180 degrees. We will come back to that later. Okay. So, now two position motion generation, you can solve it without a linkage by just pivoting at the pole, okay, or you can use a 4 bar or a slider crank or double slider, whatever. Mostly we will look at the 4 bar. So, the other practical problem that we usually encounter is where you want the rocker to move through a certain angle, move between two positions subtending a certain angle, okay, and you want the input to be continuous. So, I want this to rock back and forth between these two limit positions. Okay. So, I want to design, so let me state the problem. I want to design a crank rocker. So, basically design a 4 bar linkage, or I will just design a crank rocker, which means it should satisfy the Grashof criterion and the input should be the shortest link to move the rocker through an angle theta. Okay. We will first do this and then we will look at, and I want to do this with equal time forward and backward from a constant speed motor input. Very common problem that you would encounter. Okay. So, I give a continuous input using a motor, or could be a hand crank, although it is far more difficult to crank with a continuous speed, hand crank. So, let us say and I want it with equal time forward and backward. Okay. So, let us say this is my first position, this is my second position. I want this to move from, and this will be then OB. So, I pick my pivot OB someplace, I pick a certain rocker length which may be determined by other considerations of your application, and I say okay, now my problem becomes I want to move OB B1 to OB B2, okay, through this angle. Sorry? Yes, I am limiting those positions. I want it to move between these two and no, not beyond them. Okay, these are limiting positions. So, I am only moving through this angle theta. I do not want the rocker to move beyond that. Okay. So, that is what it is. Okay. So, now let me do this. So, I have chosen this, then now I will first do the construction, then it will become clear to you why we do that. So, I join B1 B2 and I extend it. Okay. Then I draw the perpendicular bisector of B1 B2. Okay. Then I pick some point on this line and I designate it as OA. Okay, it will become clear why I am doing that. And then I take this distance, which is half of B1 B2, and I mark that on either side. Okay. And I say that this is A2 and this is A1. Okay. So, now I say my design is complete. Show you why. So, I keep that as one fixed pivot. This is my link OA-A2. A really long link A2 B2. Then in the second position, this is my link OA A1, and now A1 B1 is overlapping from here to this point. So, you can see that as the link OAA moves by 180 degrees, okay, I have moved from OB B2 to OB B1. The rocker has moved from OB B2 to OB B1, and then now when this moves back again, I move from OB B1 to OB B2, and because I am moving an equal angle and I am running it through a constant speed motor, the time taken to move from A1 to A2 is the same as the time and therefore B1 to B2 is the same as the time taken to move from A2 to A1 or B2 to B1. So, essentially I have constructed it through simple geometry, the two extreme positions of the linkage. How do I know it is a crank rocker? Right now I do not know. I have to check. What do I have to check? I have to check the, so my linkage here is OA A, A1 B1 OB in one position, or OA A2 B2 OB. Those are the two extreme positions. AB will be equal. Why is AB equal? Because this distance, okay, this is the perpendicular bisector, right. So, that is what I am taking here. So, OA A1 equals OA A2. So, if I look at this, I can easily show that this distance is the same as A to B 2. Okay. So, this is link 3. A 1 B 1 is this is link 3, this is link 2, that is the length of the crank, and then link 4, this is link 4, link 1 will be the distance between OA and OB. So, now I have my 4 link lengths. So, I have to check Grashof criterion. I have to ensure that L2 is the shortest link and S plus L is less than P plus Q. If these two conditions are satisfied, then my just looking at the two extreme positions, I know my linkage will behave the way I want it to. That is, I can give it a continuous input and have the rocker move between these two limit positions. Okay. So, this angle again is specified, theta is specified. So, I can take some length for O4. So, that was a free choice. So, you can see that I made a lot of decisions here. Okay. I had the freedom to choose several things here in this design. I chose where to locate OB, then I chose my rocker length. It may be given to you, you may have to choose it. The angle theta was given to me. Sometimes they will tell you what the initial position should be. So, the orientation of link 4 may have been given. Okay. So, I might have said no, you have to start with this at a particular angle, okay, or that may be a free choice. Then B1 B2, where I locate the pivot, that also is a, so basically the length of link 4 was a free choice. Then it had to be located on the line joining B1 B2. So, that was not a free choice there. I had to locate OA somewhere on that line. So, I had an infinity of choices on that line. So, I located it at some point OA. Okay. If I can locate something freely in a plane, how many choices do I have? I have infinity square for a point on the plane, because I have the x coordinate and the y coordinate. If I am locating on a line, I have an infinity of choices. So, I have this. So, this was also a free choice. Was the length of OAA2 a free choice? No, it was half B1 B2. So, that was no longer a free choice. Okay. So, once I know this and I know where I am locating B1 and B2, the length of the shortest link becomes determined. Okay. And you can see here that if I take this entire linkage, I have these link lengths assembled like this. If I orient it anywhere in the plane, in any which way, I will still get the same input output relationship. Okay. That is something that you will see with all function generation problems. Okay. Because the angular relationships between the input and output link are what you are concerned with, and that does not change when you change the. So, I could design this and then finally orient my linkage such that my OA OB is horizontal, which is fine. Okay, it will change the orientation of the other things. So, this is the case for the. Now, how can I use this for the original problem that I had, which was, I have this, let me just call it C1 D1, C2 D2. I have this rigid body that I want moved from C1 D1 to C2 D2. Can I limit it to do those two positions using what I just did? How would you do that? Not you, Jayant, you know. How will you consider this as a follower?
What we did for the pole first one.
Pole. So, remember that this, if I can find the pole for this motion, then essentially this becomes a rotation about the pole. I do not know how well this will work out, but let me try. Okay, not bad. Okay. So, then essentially this problem becomes, if I this problem becomes moving this rocker, okay, P1 to C1 to P1 to C2, right, because if this line moves here, that it is all part of the rigid body. So, everything will rotate by the same amount. So, if I am able to rotate this through this angle and limit that rotation to that, then I can move this rigid body. So, essentially I will move C1 D1 to C2 D2 and back, and now I have also limited the motion. So, I can pick my B anywhere on this rigid body, okay. I could pick it here, for example. I don't it does not necessarily have to be on the line P1 to C1. So, I can pick B1 here. Now, because this is a rigid body, I have to maintain the same relationship here, okay. I have to locate it the same way with respect to, sorry, which I have not done here, somewhere here, okay. So, then I can use this, again do my construction similar to what I did earlier, okay. Find the midpoint of B1 B2 or find half of B1 B2, use that as my crank length and complete my crank rocker synthesis. So, I converted the motion generation problem into the dead center, rocker output dead center problem, because I had only two positions and I wanted to limit it to those two positions, and I can now run it with a continuous rotation motor, okay.